Example 8.8, walking a horizontal beam. The problem is a uniform horizontal beam 5 meters long. So the center of mass is going to be at 2.5 meters and it weighs 300 newtons. So I'm going to put 300 newtons right here. Its direction is going to be down. So that's a negative 90 degrees clockwise. And in this situation, the angle, the R is pointed in the x direction. So this is also negative 90 degrees. All right, it's attached to a wall by a pin connection that allows the beam to rotate. Its far end is supported by a cable that makes an angle of 53 degrees with the ground. So I'm going to write in the cable. And the cable's tension is aimed 53 degrees this way, so 180 minus 53 is 127 degrees from the horizontal up to there. Okay, and if a person weighing 600 newtons, so we'll have another row for the person, and he will be 600 newtons, stands 1.5 meters from the wall, and he will also be aimed straight down. Find the magnitude of the tension in the cable and the components of the force. So that will be tension, and then the force exerted by the wall on the beam. So we will have one more row here of the wall. The R for it is going to be 0 because it's this point here. Force is unknown. This is not applicable, and this is not applicable. Okay, so let's kind of set up our equation. Oh, R for the cable, we know that it's at 5 meters. So we can figure out our torques, and then our total is going to be 0 on all of those. So what do we got for torques? We got 300 times 2.5 times the sine of negative 90 degrees, which is negative 1. So the beam weight will give a clockwise torque of 750 Newton meters. 5 times the sine of 127 came out to be 3.9931775. I'm going to round that to 3.99, and that is counterclockwise. And then the person exerts a torque of 900 Newton meters clockwise. And the wall, 0 times whatever that force is 0. So we can actually calculate what the tension is in the rope is already, because the total is going to be 0, which means that negative 750 minus 900 plus 3.99t is 0. And it comes out to be 414 newtons for tension. So let's look at the force in the x direction and the force in the y direction. For the beam weight, we will have that force is going down, negative 750 newtons. For the person's weight, that force is going down at 900 newtons. No, we don't want the torque, we want the force. Sorry. Negative 600 newtons right here, and negative 300 newtons right there. The cable will be the tension This will be the tension cosine theta, theta xf, and this will be the tension times the sine of theta xf, which is 415 times cosine of 127 and 414. The x component of the cable is t times cosine of 127. The y component of the cable is t times the sine of 127. So these come out to be negative 249 newtons and 331 newtons up. The cable is pulling up and to the left. The sum of 0 minus 249 plus 0 plus the force of the wall in the x direction has to come out to be 0. So the wall is pushing 249 newtons to the right. Also, the sum of all of these values has to be 0. So negative 300 minus 600 plus 331 plus the force of the wall in the y direction equals 0. So from that, the force of the wall is 569 newtons. And so the wall is pushing up with 569 newtons. So it's pushing to the right and up. So the answers they asked for was the tension in the rope, which goes here, 413 newtons, and the force of the wall in the x component and y direction. They had 570 in the y direction. It's a little bit of a rounding off, but we got the right answer otherwise. Exercise 8.8. A person with a mass of 55 kilograms, 55 times 9.8 is 539 newtons, stands 2 meters away from the wall on a uniform 6-meter beam. So its center of gravity is going to be at 3 meters. As shown in figure 8.15d, I'll look at that in a moment. The mass of the beam is 40 kilograms. 40 kilograms times 9.8 is 392 newtons. Find the hinge force components and the tension in the wire. And so the wall, has 0 meters. The beam was 6 meters long, so we'll make that 6 meters. The theta RF is the same as theta XF, so the person is pushing clockwise, so negative 90 degrees. The beam is also clockwise, so negative 90 degrees. The wire going from R to F is positive 30 degrees, and the hinge is currently unknown. The wire's force and hinge force is unknown. The torque of the person is 2 times 539 times the sine of negative 90. And likewise with the beam is 3 times 392 times the sine of negative 90. So both of those are negative torques, or torques in the clockwise direction. The force of the person and beam in the x direction is 0. The force is negative 539 and negative 392 in the y direction. The torque of the hinge, we're multiplying that by 0, so we can eliminate that. And for the torque, and the torque of the wire is, we'll call this T for tension. Tension times 6 times sine of 30. And this will be t cosine 30, and this will be t sine 30. And the hinge, we'll call this r. This will be r cosine theta. That's the only unknown angle, so we'll just call it theta, r sine theta. So you can see these two columns have 2 or 3 unknowns in them, tr theta, tr theta. This column only has 1, so it's probably best to solve this column first. 6t sine 30. So 6 times sine 30 is 3t minus, and then 1176 plus 1072 is 2254. And that gives us t equals 751 newtons. And that is the answer to part A. Part B, we still need to solve t cosine 30 plus r cosine theta, and t sine 30 plus r sine theta. So the sum of these is 0, and the sum of these is 0. Oops. Okay. So r cosine theta is equal to negative t cosine 30, and r sine theta is equal to negative t sine 30 minus 390 or plus 392 plus 539. So all of these numbers, our sine theta comes out to be 555.5, and our cosine theta comes out to be negative 649.5. And I was just about to try to solve for theta and r, but I realize now that's actually, I've already got the answer that it was asking for, the 556 and negative 650 and the 751.